Hey students, so this week we'll be discussing chapter 7 in the class, and this chapter discusses the concept of estimation. So we're going to talk about why it is that you might want to estimate, what's the use. We're going to discuss the difference between point estimation and interval estimation. And the majority of this lecture today is actually going to be about interval estimation. Okay, so let's go ahead and talk about what is estimation. But in order to get into that, let's talk a little bit about the difference between population parameters and then sample statistics. Now, I'm sure you've all seen studies that have talked about the average income of all adult Americans, or talked about the unemployment rate, or talked about, the percentage of Americans who may be, favored increasing affirmative action programs, or the percentage of Americans who would vote for Donald Trump or Biden or Harris or whoever may be the current, person running for president for either side, right? Now, when you hear this type of information, I think it's important that they to understand that they don't actually survey all Americans, right? The American population is approximately 350 million people, so you'll never be able to actually, survey and get data for all Americans. So what we do is we do this process of estimation where we estimate, you know, um, these population parameters as we refer to them as, and I'll get into the definition coming up. But we estimate the percentage of Americans who are unemployed, right? We estimate the percentage of Americans who would vote for Biden or Trump or Harris, right? We estimate, the average income of all working adult Americans, right? So we don't study the entire population. Okay. So, like I said, when you see NBC polls, when you see CNN, Fox News, or Gallup, or even what we're using in our class, which is the General Social Survey, what they do is they take sample statistics to estimate, population parameters. So what is estimation? The definition, as you can see in the second bullet point, estimation is a process whereby we select a random sample from a population and use a sample statistic to estimate a population parameter. So what we're essentially doing here, we have a population. Let's just say that our population is 350 million Americans, right? So it's like these dots essentially represent 350 million people, right? Now, there is no way that we can study all 350 million people. So what we do is we take a sample. So we take maybe like a few thousand, right? Which is actually that's probably a little bit too many dots. Yeah, so say we take a few thousand, okay? And then based upon the information that we get from that sample, we then take this and then we infer, and we're going to talk about inferential statistics as well. So we infer about the population based upon the sample that we pulled, right? So we basically make assumptions about the population that we're looking at based upon the sample data that we pulled from that population. Okay. So why do we estimate, again, as I already discussed, it's too expensive to study the entire population most of the time. It's too time consuming. And in a lot of situations, you just might not have all that information, right? So we estimate for those reasons. Like for example, if we were trying to study the entire United States, I mean, how are you going to get every single person, right? You have people who kind of come and go, people who are living abroad, some people just might not answer the survey. A lot of people don't answer the census, even though it's legally required. So there's problems actually collecting all that data. Okay, so now there's two types of estimation that you might see when you look at news polls or when you look at scientific studies, right? Now there's point estimation and then there's interval estimation. Okay, now like I said, the majority of this class, we're going to be talking about interval estimation. Okay, but let's just discuss really quick because outside the scientific literature, you're most likely to run into point estimation, just to make things simple for people, okay? So when you see studies and polling data conducted by, news organizations, or when they report the data, they usually report point estimation, okay? Now, point estimates are sample statistics that are used to estimate the exact value of a population parameter. Now, in interval estimates, we basically use a range of values within which the population parameter may fall. Okay. So let's see. So what do I mean by that? So a point, let's just say, we're gonna guess, let's just say that sample data has suggested, this is just information that I've gotten in the past, that the average income of all working adult Americans is approximately 60,000. Okay, so let's just say it's about 60,000. Now, so that's a point estimate. Now you might ask yourself, well, 60,000, that's a very specific number. It's not 60,001, it's not 59,998, 60,000, right? So point estimate is just one exact value, right? Now, interval estimate, as you saw from the PowerPoint, it's basically gives a range of values within which we believe the population parameter falls. So interval estimate, instead of giving the exact value, like exactly 60,000, an interval estimate might be somewhere between like 55,000 on the low side, then 65,000 on the high side, right? Now I'm just making these numbers up right now. That's not how you do it. You're going to learn how to actually create an interval estimate as we progress through the class, but I'm just using this as an example. Let's just say it's somewhere between 55,000 to 65,000, right? Okay. So now we have a range of an interval, right? A range within which we believe that the average income of all adult Americans falls, right? Instead of giving the exact number, we have a range that we believe is going to fall within. And that's what you're more likely to see in scientific literature. Okay, so that's the difference between a point estimate and an interval estimate. Okay, now, some things about estimation. So there's two terms that we should define. One, confidence interval, and then two, confidence level. So what is a confidence interval? So a confidence interval is a range of values which is defined by the confidence level within which the population parameter is estimated to fall. That probably doesn't make a lot of sense right now, but let's read this next bullet point, and then we can help flesh it out a little bit better so it's easier to understand. Now, the confidence level is the likelihood that we're going to express as a percentage or probability that a specified interval will contain the population parameter. Now, I know what you're thinking yourself. That doesn't make sense. So let's try to break this down in a way that I think helps make sense. Again, I'm gonna do this as an example. This isn't the way that we do it. You're gonna learn how we do it, but I just want to use this as an example to kind of illustrate the relationship between a confidence interval and a confidence level. Okay, so we are, let's just say, on the Palm Desert campus. We're taking this class online. Let's just say we're on the Palm Desert campus, okay? Now let's just say that you have another class at the Indio campus, okay? Now, let's just say that we want to know how long it takes us to get from the Palm Desert campus to the Indio campus, right? And driven it multiple times. I already guess, me guessing, I would say it's probably 25 minutes, just to be on the safe side. So I'll just say it's 25 minutes. Okay, so, and I'm just gonna represent this as like, let's just say I took a sample of the class, I'm just asynchronous class. I'm just talking to myself right now. Let's just say I took a sample of the class, and we said that in general, it takes us 25 minutes to get there, right? So let's just say 25 minutes, okay? Now, let's just say that I wanted to express how confident I am in this, right? Let's just say that I believe it's going to be 25 minutes, but let's create an interval around this 25. Let's just say that we expand this interval from anywhere between 24 minutes and 26 minutes. Okay, so that's my interval. So this right here is my interval. So how is that related to a confidence level? Now, how confident are you that you would make it from the Palm Desert campus to the Indio campus within 24 to 26 minutes? Now, you might say, well, that's a small interval. I'm not that confident. I mean, I could run into a bunch of red lights and it might take longer. Or kind of feel like when you're driving down Fred Warren, it's either all red or it's all green. There's never like red and green. It's just all red or all green. So you might take 35 minutes if you're running all reds, or maybe you get there in 15 minutes if you just hit all greens, right? And you're speeding. Probably shouldn't do, the cops are there. Red Warren, they're just looking for people to pull over. Okay. So I'm not really confident in this. Let's just say that I'm like 40% confident that I would make it within this specified interval, right? So that's my confidence level. So this right here is my level. Now, how would I go about making myself feel more confident that I would make it within this interval time? All right. Well, what I can do is I can expand the interval. So instead of 24 to 26 minutes, let's just say I open it up from anywhere between 20 and 30 minutes. 20 and 30 minutes. Okay, now, do I feel more confident that I can drive from the Palm Desert campus to the Indio campus in somewhere between 20 and 30 minutes? I feel pretty confident that I'd make it within that specified interval. So now my confidence level goes up, right? So instead of being 40% confident, I'm 80% confident that I'm going to make it within that time frame. Again, I'm just making up numbers. This isn't how you do it. But I just want to show you how this confidence level relates to the interval. Now, let's just say that I wanted to be even more confident. I don't want to miss my class, right? So I want to be more than 80%. I want to be like 90, 99% confident, right? That I'm going to make it there within that specified interval. So what I can do is I can stretch it out some more, right? Let's just say that I'm going to say 15 to, let's just say 35. Well, say I'm about 90% confident that I'm going to make within this time frame. Or let's just say that I want to maybe expand it out to 10. So between 10 and 40 minutes. 10 and 40 minutes. Well, I'm like 95, percent confident. And let's just say we go all the way to like 5 minutes. I'm pretty sure I'm not going to make it faster than 5 minutes. And it shouldn't take me more than 45 minutes to get from the Palm Desert to the India. So at this point, I might be like 99% confident that I'm going to make it within this time frame. Now, to kind of like expand upon this relationship between a confidence interval and a confidence level, I'm very confident that I'm going to make it within this time frame. Okay. Now you might say to yourself, well, I'm 100% confident that I would make it there. Well, I'm not 100% confident. Again, maybe I speed and I get pulled over by the cops. So I'm not going to make it within 45 minutes if I get pulled over by the cops. Or if my tire, if I get a flat and I have to change my tire or something like that, well, I'm not 100% confident. So with confidence levels, we're never 100% confident. We never have like 100% confidence level because we're ultimately dealing with statistical data, right? So we're using data that we're pulling from a population and we're kind of inferring to the population based upon this statistical data. So we're never going to be 100% sure. We're never going to be 100% confident, right? So this is kind of talk about the kind of relationship between confidence level and confidence interval. Now, what might be one of the problems with like 99% confidence level? You might say to yourself, well, in statistics, we usually use 90, 95, and 99% confidence level to build our intervals. And I say to yourself, well, why wouldn't you always just want to be 99% confident? Well, I don't know if you noticed what happened to that interval. Well, and you should notice, you just saw it, right? But what happened to the interval when our confidence level grew? Our interval expanded. Now, what's problematic about that? Well, when your interval expands, you lack precision and specificity, right? So if you were to ask me how long it takes to get from the Palm Desert campus to the Indio campus, and I tell you it's going to be somewhere between 20 and 30 minutes, that's helpful, right? You can determine based upon that information how long it's going to take you to get there. If you need to make your class from the Palm Desert campus to the Indio campus, give yourself a good 30-minute break or 40-minute break or 45-minute break. But let's just say tell you it takes you anywhere between 1 minute and 1 hour. Well, then it's just like, that's not useful, right? So when your interval is too big and it lacks specificity, it lacks precision, and if it's too big, it's just not helpful anymore, right? So you kind of want to touch a balance between the confidence level and the confidence interval. Okay, so that's confidence interval and confidence level. Okay, so when we use confidence intervals to estimate population parameters, we can also evaluate the accuracy of this estimate by assessing the likelihood that any given interval will contain the mean, the population mean. So we already talked about how the confidence level connects to the confidence interval, right? And when we express it as a percentage or probability, and we call it a confidence level. That is, how sure you are or how confident you are that that interval contains the actual population parameter. Okay, now, if we wanted to be 95% confident, all random sample means would fall within plus and minus 1.96 standard errors. And if we wanted to be 99% confident, all random sample means would fall within plus or minus 2.58 standard errors or z-score. Okay, now, right now, what you need to know, and I'll explain this a little bit later, but what you need to know right now is that the three most common confidence intervals that we're going to use is 90, 95, and 99. Okay, so the three most common confidence intervals that we're going to use are 90%, 95%, and 99%. Okay, now, if you remember from the PowerPoint, I should have just put this on the PowerPoint, but too late now, so I'm gonna explain it right now. The PowerPoint said that the 95% confidence level relates to a standard deviation of 1.96. Okay. Now, that it also said that the 99% confidence level corresponds to a z-score or standard deviation or standard error, the mean of 2.58. Now, the 90% confidence level corresponds to a z-score of 1.65. Okay. That's the three things, that's the three numbers that you need to know. Okay. Now, you might ask yourself, why does the 95% confidence level correspond to a standard error or z-score of 1.96? So if you remember from last lecture, we were talking about the standard normal table, right? And how it is that the sampling distribution is essentially a normal distribution, right? That follows all the same properties and all the same numbers. So if you remember, we did this, we drew a standard normal distribution, right? We have a mean, right? Now, we remember that .26% of all random sample means are going to fall within +1 or and -1 standard deviation. .46% of all random samples are going to fall within 2 standard deviations or 2 standard errors above and 2 standard errors below, right? The mean. And .9972, running a little bit out of room. Hopefully you all can stick with me and understand this. 99.72% of all random sample means are going to fall within 3 standard errors above and 3 standard errors below the mean. Okay. Now, so if we know we're dealing with a 95% confidence interval, right? Well, we know that that corresponds, or 95.46% of all random sample means are going to fall within 2 standard errors above and 2 standard errors below, right? But I didn't say 95.46 now, did I? I said 95%, okay? So if I wanted to do 95%, okay, 95% instead of 95.46, so 95% as opposed to 95.46, what I would have to do is I would have to find the z-score that corresponds to a 95% confidence level. Right. Now, if you remember the standard from the standard normal table, we don't actually find 95%, right? It doesn't go that high, right? So what we'd have to do is we'd have to cut the distribution in half, okay? Hopefully y'all remember this. You kind of did it with the last homework. You should have done it with the last homework. So what you would do is you would go to the standard normal table, you go A, B, and then C, right? Now with the B or the C, it doesn't really matter, but what would you be looking for if you cut that 95% in half, okay? What you could do is you could use a calculator. It's going to be 47.5, I believe. I'm just going to check my work. 95 divided by 2 is going to give you 47.5. So what you're going to be looking for is the proportional equivalent of 47.5, right? Cut 95% in half. So we take 95%, I'm going to write it over here. 95 divided by 2 is going to give you 47.5. Now, again, this is represented as a percentage, but we don't want it as a percentage. We want to convert it to a proportion, right? So once we convert a percentage to a proportion by dividing by 100, we are going to get the proportional equivalent, which is equal to 0.4750, right? So what we're going to be looking for in the B column is 0.4750, right? Now, if you remember, the B column combined with the C column needs to add up to 0.500, right? So I already know that what we're going to see in the C column is 0.0250, okay? Now, if I were to then look into the standard normal table, I'm going to try to pull it up here. Okay, hopefully you all can see the standard normal table. If we zoom, okay, maybe we can't zoom in. Okay, there we go. we're gonna look for in the B column 0.4750. And in the C column, we're gonna look for 0.0250. When we find out, what do we see in the A column? That is 1.96, okay? So having said that, I would put 1.96 in the A column, and that would be our Z-score equivalent. That'd be our standard error equivalent to 95%. And you would do that exact same thing with 99%. If you know, you would take 99%, cut it in half. Let's see. We would get 2.58, right? So you would take 99% and you would 99% divided by 2. You can do that in a calculator if you want to check the work. 99 divided by 2, you're going to get 0.4950. And when you find what's equivalent to 0.4950, you're just going to go with 2.58. But same thing, if you were to do the 90% confidence level, 90% divided by 2 is going to give you 45% or proportion equivalent of 0.4500, which we're going to find about here, right? And then, so 0.4500, and then that would correspond to a Z-score of 1.65. So that's how we essentially go about getting those numbers. Okay, so let me go back to my PowerPoint. Okay, so that's how we got that. So we, for the 95% confidence level, we got 1 point. And again, if you wanted to do this, you could do this exact same thing for the 99%. You take 99, divide by 2, you get 0.4950, put that into the B column, go find that in the standard normal table, and you would find in the A column 2.58. If you were looking at for the 90% confidence level, you would take 90% divided by 2, right? As you see our work down there. You would get you get 45%, which you convert to 0.4500. Find that in the B column, it will correspond to 1.65. So that's essentially how we get these numbers for 90%, 95%, and 99%. That's how we get those corresponding Z values. Hopefully that makes sense to you all, because you will have to do that with the homework this week. But honestly, if you're doing scientific research and you don't remember how we got the corresponding Z values, you could probably just memorize that 90% corresponds to 1.65, 95 corresponds to 1.96, and 99 corresponds to 2.58, a Z-score of 2.58. Because those are the traditional confidence levels that we use in the social sciences. Okay. Hopefully everybody here is still with me. Okay, so like I said, what we want to do is when we're constructing a confidence interval, we want to construct an estimate of where the population mean falls based on our sample statistic. Okay, so again, what we do is we pull a sample mean, right? We pull a sample mean. And then we build our interval based upon how large we want our confidence level to be. So if you want 90% confidence level, our interval is going to be this big, more or less, right? 95 is going to be bigger. 99 is going to be bigger. Okay, keeping everything else equal. Okay. Okay, so far we've only kind of theoretically talked about how to actually create a confidence interval, right? And we talked theoretically about the relationship between a confidence interval and confidence level, but we haven't actually talked about the actual equation. Okay, so now I was unaware of this, but basically what's going on is my iPad is altering my PowerPoints. So, but we can still figure this out. Okay, so what we want to do, see if I can change the color. So the formula for this is CI, so the confidence interval is equal to plus and minus. Okay, so it's not a plus or minus, it's a plus and minus. Again, remember, we're going to take the confidence interval formula, right? That we're going to both build it up above the mean and below the mean. So we're gonna have an upper bound of the limit, we're gonna have a lower bound of the limit. So we need to both add and subtract, okay? Okay, now we have the Z confidence interval. Actually, hold on. This, let me erase this. Here we go, confidence interval. Sorry, confidence interval is equal to, now it goes plus and minus the Z. Sorry, my PowerPoint got altered a little bit. The Z times the standard error of the mean, okay? So like I said, what we're essentially going to be doing is we're going to pull a sample mean, and then we're going to build up both above and below. So we're going to have an upper bound of the confidence interval and a lower bound of the confidence interval, okay? Now, now the Z-score that we choose depends on the desired confidence level, okay? So for example, to obtain a 95% confidence interval, we would choose a Z of 1.96. Because as we already discussed when we talked about how to find the corresponding Z value, the Z is equal to, the A column for whatever confidence level we choose. Okay, so we know that a Z of 1.96 corresponds to a 95% confidence level. Okay, so if we were to go back to this equation, that Z, if we were using a 95% confidence level, would be 1.96. The sample mean, we'd have to get that from actually sampling, and then the standard error of the mean is again something we'd actually have to pull from our sample data. Okay, now having said that, you as a researcher get to choose how confident you would like to be. A simple way to do this is just calculate all three of them, the 90, the 95, and the 99% confidence level if you want to. And you can kind of explain that in your actual study. Okay, so what are the steps to constructing a confidence interval? Okay, so to determine the confidence interval for means, follow these steps. Now, the first thing that you're going to do is you're going to calculate the standard error of the mean. And hopefully you all remember how to calculate the standard error of the mean. If not, we'll actually talk about that coming up. The second thing we're going to do is we're going to decide on the level of confidence and find the corresponding Z value. Okay, so 90, 95, 99, again, it corresponds to 1.65, 1.96, and 2.58. Then we can calculate the confidence interval by using that equation that I showed earlier. And then we're going to then go about interpreting the results. Okay. All right, so the standard error of the mean, hopefully you all remember how to calculate this. Now don't get confused because this looks exactly like this, but they're not the same thing, okay? This, the population standard deviation, and then this is the standard error of the mean, which is something we discussed last week or last class. So what you would essentially do is you would take the population standard deviation, and then you would divide by the square root of the sample size. So that N is the sample size. Okay, now when you're doing sampling, when you're sampling, Um, typically the case that the standard error or the population, uh, the standard error can't be found because the population standard deviation is not known. Why, you might ask? Well, if you're sampling, you don't have information about the population. We already talked about that. The population is too big, it's too large, it's too time consuming to find all that data. And a lot of times we can't find the whole data, right? So for example, if we're trying to find the average income of all Americans, the American population is too big for us to capture all that data. So we sample, right? So since we don't have the population information, we don't have population standard deviation. And if we did have the population standard deviation, then all of this would be pointless because we'd already have the information about the population. So we wouldn't be sampling, right? So what we need to do is we essentially need to estimate the standard error based upon the sample data, right? So this is what we refer to as the estimated standard error. Hopefully everybody's still with me. Because we don't have the population standard deviation, we need to pull the sample standard deviation. So this is the sample standard deviation. And then this is same thing as last time. It's the sample size. Hopefully everybody's still with me still. Okay, so let's give it a shot. Okay. So let's just say we're calculating the standard error of the mean. We are looking at the average age of 500 COD students. Now let's say that the standard deviation for our population of COD students is 2.5. So we actually have the population standard deviation, so we can actually use the actual standard error, but most of the time when you're sampling and you're using sample data, you're not gonna have that, but this is just, we're just practicing, right? Okay, so let's just say that our standard deviation for a population is 2.5. We can now calculate the standard error of the mean based upon this equation, right? So if we know that the sample size is 500, where would we put that? We would put that where the n goes. So if I want to rewrite it on my whiteboard, this, oh yeah, and the difference between the population standard deviation and the standard error of the mean is this line. So if I write that line over that y, that is the standard error of the mean. So we know that we can get that by taking the population standard deviation. There's no line over the y, so we know there's a population standard deviation. Dividing it by the n, the sample size, we know that the sample size is 500. Let me write that a little better. 500. And then we know, based upon what we saw from the PowerPoint, that the standard deviation is 2.5. Based upon this, we can calculate this. Now, what we're going to do is we need to take the square root of 500 first, and we are going to get 22.36. There's some other numbers, but we're going to round to the 100th because all of the other numbers, they go too far. Okay, now that we have 22.36, we're then going to take 2.5 and we're going to divide by 22.36, and we should get 0.11. 0.11 as our standard error. Okay, so we've done the first step, we calculate the standard error. Calculate the standard error. Now, if you remember, what's the next step is to decide on the level of confidence and find the corresponding z-value. So let's just say we want an 80% confidence level. Okay. Now, what would we do? We know it's not 90, we know it's not 95, we know it's not 99, right? So what we'd have to do is we would have to draw what I would do is I would draw the normal distribution out, right? To 80%, right? But we're not gonna find 80% in the standard normal table. We're gonna go A. We're going to find 80 divided by 20, or divided by 2, gives us 40%. To get 40%, right? And then to convert it to a proportion, we're gonna get 0.400, right? So that's what we're gonna be looking for in the B column. This, the B and the C column together needs to add up to 0.500, so we know that the C column is gonna be 0.10. So that's what we're looking for, okay? Now, if I go back to the standard normal table, and I look for 0.400 in the B column or 0.100 in the C column, what I'm gonna see, this isn't the exact number, but it's close. The closest number that we can find to 0.4000 is the closest number that we can find to 0.1000. So that corresponds to an A of 1.28, okay? So now I know that my Z value is 1.28. So my Z value is 1.28. Okay, so now that we this up, CI is equal to the sample mean plus and minus the Z times the standard error of the mean. And let's just say that the confidence interval, let's just calculate this if we have a sample mean of 20.8, okay? So we know that we have, I don't know, I don't think I have enough room here to do this all, so I think I'm gonna go to the whiteboard. So we're gonna go a CI, so the confidence interval formula, equal to the sample mean plus and minus the Z times the standard error of the mean. I like to rewrite the formulas before I start plugging things in, just so I make sure I have the formula right. Even I messed up earlier on the formula, so you want to like just copy down straight from the textbook. So now that we can start, now that we have that down, we can start plugging things in. So sample mean, we stated from the PowerPoint that the sample mean is 20.8. So we're going to put 20.8 here. Plus and minus. Now the Z value, if you remember, we calculated that, and then that is 1.28. We're going to plug in, for the Z, we're going to do 1.28. And if you remember our other calculation, our standard error is 0.11 or 0.11. Okay, so now that we have that, we can now calculate this. So what I want y'all to do is, maybe pause this and then calculate this, and then we can come back. But I'm just gonna calculate it, assuming that you paused the video. Okay, so what we're gonna do, follow the order of operations. PEMDAS, please excuse my dear Aunt Sally, right? Whenever we do parentheses, exponents, multiplication, division, then addition, subtraction, we calculate our equations, just like we're reading a book, from left to right, top to bottom. So now we do have the plus and minus symbol left to right, but we have a multiplication before that. So we need to do that first. We're gonna do 1.28 times 0.11, okay? 1.28 times 0.11, then that should give us 0.14. Okay, now, we can go ahead and just write this out right now. Let me give myself a little bit more room with this. 20.8 is our sample mean, right? We go to upper bound and a lower bound. Okay, so we're gonna go upper. A lower bound. Okay, so we're gonna do 20.8 plus 0.01 plus 0.14 gives us 20.94. Now, in order to get the lower bound, we're not gonna add, right? We're gonna do 20.8 minus 0.14, and we're gonna get 20.66 on the lower bound, right? So that's essentially how we went about constructing our confidence interval for 80% confidence level, okay? Now, so that's for 80%, right? That's for an 80% confidence level. Let's just say that we were to do that exact same thing, but instead of like an 80% level, we wanted a 95%. Now, again, it's almost the exact same formula, right? But the only real difference is that our confidence level has changed. So instead of doing 1.28 like we did last time with 80%, we would use, if you'll remember, 1.96, right? So our Z value would be 1.96, and then it'd still be the same standard error, right? So what we do, what do you think is gonna happen? Is it gonna make it a bigger interval or is it gonna make it a smaller interval? Now, hopefully if you'll remember what we talked about theoretically earlier on, is that a bigger or a larger confidence level creates a bigger confidence interval. Okay, so what we're gonna do is 1.96 times 0.11 is gonna give us 0.2, I'm just gonna round it to 0.22, okay? What we're gonna do, so we're gonna do 0.22, 3.8 plus 0.22 gives us 21.02. And now 20.8 minus 0.22 gives us 20.58. Okay, so let me get back to this. I believe there was a little bit of a technical problem and it may have stopped recording some things. Anyway, so what I was trying to illustrate before we got cut off was that if you calculate 95% confidence level, what happens is the interval expands versus the 80%, it's a little bit of a tighter, more specific interval, but your confidence level is substantially lower, right? So as you can see, 20.66 is the low side on 80%. For the 95 is 20.58. The upper bound of the 80% is 20.94. With 95% confidence level is 21.02. So as you expand your confidence level, you also expand your interval. Okay. Okay. So that's how we went about calculating the confidence interval for that data. Okay. So now interpret the results. What we would say in this situation is we can be 80% confident that the actual mean age of all CID students is not less than 20.66 years old and not greater than 20.94 years old. Now, again, we can never be 100% sure whether or not the population mean is actually contained within our confidence interval. Again, we're dealing with probabilities, we're dealing with statistics, we're not dealing with absolute facts, okay? Hopefully everybody's still with me. Okay, so what can we do? We can reduce the risk of being incorrect by increasing the level of confidence, right? If we increase our confidence level, what happens? Our interval expands, okay? And when we use the highest level of confidence, let's just say a 99% confidence level, there's only a 1% risk that we are wrong. The specified interval does not contain the true population mean, okay? Now, sample size and confidence intervals. Now, I already told you that if you increase your confidence level, what happens is your interval increases. Okay. Now, let's just say that instead of increasing our interval, what else can we do to make sure that our interval is to say that our interval is precise, more specific? So what we can also do is we can increase our sample size. So researchers have the ability to increase the precision of their estimates, meaning the confidence interval is smaller by increasing our sample size. Okay. So larger samples will essentially result in smaller standard errors and therefore in sampling distributions that are more clustered around the population mean. Now, hopefully that makes sense. So for example, when we're calculating that confidence interval, right? So the 500 of the sample size is in the denominator. So holding all else constant, what would happen is if you increase the denominator, if you increase the sample size, the standard error will be smaller. Now, if the standard error is smaller, if you look at it into this equation, you're going to see that the interval is going to be smaller too. So what do I mean by that? Let's just say that instead of having a sample size of 500, just say that we were to recalculate this, 2.5, so everything's staying constant except the sample size, 1,000. Find the square root of 1,000. And it's going to be 31.62. So we already see that that number is bigger, right? Which means that the 2.5 divided by 31.62. So that number is going to be 0.08, right? So smaller than 0.11, which means that your interval is going to be smaller as well. Okay, so that's just one of the ways that you can make your estimate more specific, make your interval more specific and more precise. Okay, now let's talk about how to calculate confidence intervals for proportions and percentages. So the procedures for estimating proportions and percentages are identical, right? Similar to the means, but slightly different. But the sampling distribution of proportion underlies the estimation of population proportion from sample proportion. Now, it's the same exact logic and the same exact theory that we used when we were calculating the sampling distribution of means, right? So the sampling distribution of proportions, pretty much the same thing, same exact numbers, right? So we're not going to rediscuss that. So how do you actually go about calculating a confidence interval for proportions or for percentages? So what you would do, and you're going to have to do for the homework, you have to do it for both means and proportions for this week. So the general formula for constructing confidence intervals for proportions is any confidence level is, so the CI is equal to, in this situation, my iPad didn't alter my PowerPoint. So is the P, if you remember this, P is the sample proportion plus and minus the Z value. The Z value, again, doesn't change, right? If we're looking at 90%, Z value is 1.65, 95, 1.96 for the Z value, 99% confidence level is 2.58 Z value. So that does not change, okay? And then the estimated standard error of proportion, so that is different, right? So we already talked about how to calculate the standard error of the mean. Now we need to talk about how to calculate the standard error of proportions, slightly different. Also, another thing that's important when you're actually doing the homework is that when you're calculating, you're going to see percentages, right? Like, the percentage of people who voted for Democrats or Republicans, yada, 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 right? In order for this formula to work, you need to take that percentage and then convert it to a proportion and then put it into the formula. Because if you don't, it's not going to work because it's for proportions, not for percentages. Okay. So that's one other thing that I think you should pay attention to when you're doing the homework. Okay. So first thing, calculate the standard error of the proportion. Okay. So that's for estimating proportions. 2, decide on the level of confidence, like I said, 90, 95, 99. Calculate the confidence interval, and then interpret the results. Okay, so we're going to use data from the textbook. Let's just say that the textbook looked at the results of the CBS News poll election on satisfaction with the election outcome. So for our study, the sample proportion, sample B, is 0.50, so which is essentially equal to 50%, right? So you take the 50%, in order to convert it to a proportion, we divide by 100, we would get 0.50. Now our sample size, so the sample size was an N of 1,048 people responded, okay? So we're gonna find the estimated standard error proportions based on this information. Okay, so again, I kind of left something out, but basically the only thing that it left out was the estimated standard error of proportion is equal to the square root of the sample proportion multiplied by 1 minus the sample proportion divided by N, which is the sample size. So if we were to rewrite this with the actual data that we've been given from the PowerPoint, we would come up here. You're going to do SP is equal to the square root of the proportion multiplied by 1 minus the proportion divided by the N. So let's fill in what we know. Square root. What is our proportion according to the PowerPoint? 0.50. Okay, so 0.50. I'm going to put 0.50 here. Now, we also know that we have 1 minus the portion, which is 0.50 as well. And then we know our sample size was 1,048, right? Good. So now we have everything plugged in, and what we can do now is we can solve. So if you want to pause this, go ahead and solve it. I'm assuming you paused it already and you solved it. Let's go ahead and check your work. So we know 1 minus 0.50 gives 0.50, so it's 0.50 times 0.50 divided by 1,048. So 0.50 times 0.50, I believe, is 0.25. 0.25 up here divided by 1048. Now, I'm just gonna go here. After we do that, we get some just astronomical number, 0.00023855. It keeps on going, but it's not going to do all that. So we're going to take the square root of that. And we are going to be left with 0.015. So our estimated standard error proportion would be 0.015. Okay. So we calculated our estimated standard error proportion. Okay. Now I just said, let's just go ahead and use the 90% confidence level and find the corresponding Z value. Okay. So we're going to have a CI, if you all remember, is equal to sample proportion plus and minus the Z value times the estimated standard error proportion. Now, we already know we know actually all three of these. So CI is equal to the sample proportion of 0.50 plus and minus the V, which for, I think we said 90%, should be 1.65. And then our estimated standard for 0.015. Okay, so now we have 0.015. You all might be thinking to yourself, why did you round to the thousands instead of the hundreds this time? Because what we're going to do is we're going to multiply by 100 to turn it back into a percentage. So I just want to give myself a little bit of leeway. Okay. Now again, we're going to follow the order of operation, PEMDAS. Please excuse my year at salary. We have multiplication over here to the right side. So we're going to go 0.015 times 1.65 is going to give us 0.0, I'm just going to say 0.025. It's going to give us 0.225. Okay. So we got our we're going to try to find our upper bound and we're going to try to find our lower bound. So what we're going to have on the upper bound is if we're going to do 0.25, 0.50 plus 0.025, going to give us 0.525. And for our lower bound, we would then subtract 0.50 minus 0.025. That's going to give us a 0.475 on our lower bound. If we were to convert these two percentages, it would be 47.5 on the lower bound, 52.5 on the upper bound. Okay. The Z value, we already did this calculation. And so what we would say is that we are 90% confident that the true population proportion is somewhere between 0.475 and 0.525 if we're talking about proportions, or we could convert that to percentages as we just did. And we could also express the result in percentages and say that we are 90% confident that the true population percentage of satisfaction with the election outcome is in between 47.5% on the low side and 52.5% on the high side. All right. Well, that was the lecture and the information for today. I don't know what's. Okay. Anyways, if you all have any questions, go ahead and shoot me an email, come to office hours, and I will help you out. One thing that I think was important to pay attention to is, again, if you're running into one of the equations and you're like, oh, I can't figure out how to calculate the standard error or the estimated standard error, the mean, you're probably looking at a proportions equation. So you need to use this the confidence interval formula for proportions. If you're looking at the equation, you're like, I cannot figure out how to calculate the estimated standard error for portions, you're probably looking at the equation that looks at means. So you're gonna have to use the equation that deals with means. Outside of that, hopefully you all got this stuff. Yeah, again, you have a question, shoot me an email, come to office hours, and good luck this week.